So the parts of your trig graph. Domain, range, period, amplitude. Need to know this. Need to know this fairly well. So here you have a picture of your sine and cosine graph. First off, the domain of your sine and cosine graph. What values can you find the sine and cosine of? Well, looking at your graph, there's no breaks in your graph. Okay, this thing goes forever to the right, goes forever to the left. It doesn't stop here. It continues doing the exact same things to the far right and to the far left. Domain, all real numbers. The range of your graph. Notice that you could actually draw a box above and below this sine and cosine function. The sine graph never gets above 1, and the same thing with cosine, and they never get below -1. So the range, and it does include, the range of both graphs is from -1 up to +1. Never gets above or below it. The period. What a period is, and you see here what's going on. The period is how long it takes for something to go through a complete cycle. You start here at 0, 0. Your sine function repeats, and it starts over here. You see that? Same thing with cosine. Let's say pick any starting point here. Let's say in science, what is a crest and a trough is what to where the crest is the highest point, the trough is the lowest point. Same thing here. What I would do is pick a crest or a trough, or pick this, what I call a point of equilibrium, that point right in the middle. See how long it takes to get back to that point. You deal with the cosine function. You're here at the crest. You're going down to the trough and then back up to the crest, and it starts over again. One complete cycle. Okay. For cosine and sine both, what's a complete cycle of those? Can you tell by looking at the graph? How long does it take, x values, how long does it take for it to repeat there? 2 pi units. Every 2 pi units, your graph starts over again. Here you've got -2 pi. 2 pi's later, look, it's back at the same spot. So the period of your sine function and cosine function are both 2 pi. They repeat every 360 degrees. Amplitude. Again, we go back to what I called a while ago, kind of a point of equilibrium. You could split this right down the middle, and it's kind of the same above and same below. This is kind of the middle point of this. Think of it like an ocean wave. Okay, the point of equilibrium is kind of the resting point. Well, there's no dent, there's no troughs, there's no crest. If you took those waves away, this is where it's resting at. To find the amplitude, it's the height from the point of equilibrium. If that was at rest, it would be, okay, from that point at rest, how high is that wave now? For both sine and cosine functions, what is the amplitude? 1. It's not the entire height. It's not the lowest point. Now you can do this. Another way of finding your amplitude is take the lowest point on your graph and take the highest point on your graph. Find the difference between those two, which in this case is 2, and then half it. So another way to find your amplitude, again, take the lowest and highest points. What's the difference between the two? In this case, like I said, it's 2. And then half it, and you get 2 divided by 2 is 1. So therefore, your amplitude for both sine and cosine is 1. Now later on, we'll talk about your tangent functions. Domain is different for tangent, because we know there's certain values that you can't find the tangent of, such as 90, 270, 450, and so on and so forth. You can't take the tangent of those because the cosine of those values are 0. You can't have a 0 on the bottom. The range, very different. Think about what the graph of a tangent looks like. This number, right, continues up forever, down forever. The range of tangent is from negative to positive infinity. The period of tangent is going to be different. We'll talk about that later. And amplitude, tangent graphs don't have amplitude. It's not a wave. A tangent graph is not a wave, so you're not going to have amplitude. So there's everything that I just said. Y equals sine of x has a period of 360 or 2 pi, and so does cosine. The amplitude of both of them are 1. The domain is all real numbers, and the range is from -1 to +1. Good there. So let's do transformations. right? Reminder, if you need one. Y'all heard this a few times this year. Multiplication. Multiplication and division. If you take a graph and you multiply your x or y, or you divide your x or y by some number, what does that do to your graph? Good. Stretch and shrinks. Addition and subtraction. What does that do? It translates it. It moves it. It translates it up, down, left, right. It doesn't change. Doesn't change the graph at all. It's identical except for it's shifted up, down, left, right. It's just shifted over. Negatives, flip. And again, it all depends on where these things are located. If it's located inside of parentheses with the x, things happen horizontally. It's happening left, right. If you add 3 to your x, you're gonna shift, and you got to be careful there as well. If you let's remind, if this was your parent function and you went from there to x minus 3 squared, if things happen to the x, it happens backwards. Minus 3 inside parentheses with that x is actually going to shift it right 3. If you multiplied that by, if you came in here inside parentheses and you multiplied it by 2, multiplication by 2 inside with the x actually doesn't stretch it times 2. It shrinks it times 1/2. You got to do the reciprocal. So that's your review before we go into these problems. Sketch the graph of y equals 2 times sine of x for x in the interval. And we're not going to go through and actually graph all these. If you wanted to graph them, you've got your table of values. Okay? Or you can use your original sine function. And let's see, let's talk about what that's going to do. It's going to be identical to your normal sine graph, except for you got that 2 out front. What's that 2 going to do? It makes it twice as tall. It stretches it vertically, for those of you that said that. It's 2 times taller, 2 times lower, I guess you could say. Here's your actual 2 graphs. I've got all these graphed ahead of time. Make our lives easier. The blue graph is y equals the sine of x. The red graph is y equals 2 times the sine of x. Now let's go through all those things again. Domain and range. Did what I just did, there we go. Change your domain? No, it's still all real numbers. Did it change your range? Yes, and you've got to know, you've got to be leery of, okay, when you do this transformation, what's it going to change? It will change your range. It's no longer from -1 to +1. It is now from -2 to +2. Did it change the period of the graph? The period is how long it takes for that graph to repeat. Before, okay, start at this equilibrium point. This blue graph repeated every 2 pi units. What about the red graph? Does it start over after 2 pi? Yes. Stretching something vertically is not going to change the period at all. Does it change the amplitude? Sure. And let's go back. One more time. What was the amplitude of sine x? 1, right? Isn't there a 1 out front of that sine x? What's the amplitude of y equals 2 times sine x? 2. Because it's twice as tall. It was 1, you make it twice as tall, now it's 2. Okay. Moving on. Graph y equals 4 times sine x. And I don't have this one graphed, but let's just talk about what it would do. Would it change the domain? No. Would it change the range? Yes. What would be your new range? -4 to +4. Good. Would it change the period? No. Would it change the amplitude? Yes, and your new amplitude would be 4. So what I'm trying to get at is that number always your amplitude? Unless it's -4. Because -4 would actually stretch it and flip it. If this number right here was -4, could you tell me what your amplitude would be? Or excuse, yeah, 4. You're not going to have a negative amplitude. Okay, so pretty much you take the absolute value of that number. Yeah, that's your amplitude. Next one, sketch the graph of -3 times cosine x. Already got it done. Transformation. Before I blow it up, let's talk about transformations. What's the 3 do? Stretches it 3 times taller. Good. What's the negative do? Flips it. So that's the only two transformations going on here. And most of these problems will work. We'll just have limited transformations like that. The blue one is your original cosine graph. Notice, again, cosine of 0 is 1, so we can tell that is cosine graph. If we shifted it over a unit there, then it turns into your sine graph. We took and we did two things. We made it 3 times taller, and then we flipped it down here. So we flipped it vertically, made it 3 times taller. So again, we go through all these things. The domain did not change. The range is now, again, -3 to +3. The period did not change, and the amplitude changed to 3. ACT questions. I've seen in the review books, I've seen in a lot of the review books, them giving you a problem that looked like this, and them just saying, what's the amplitude of this graph? How easy is that? Right? You look at the number out front, and you've got your amplitude. Same thing. Let's move on. Phase shifts. And we've done all this stuff. There's really nothing new besides just introducing the words amplitude, introducing phase shift here, period. We know domain range, all those things. So we're just really introducing new vocabulary. Graph 2 cycles of y equals sine of x plus pi over 6. Before we start, Michael, what is pi over 6? 30 degrees. So we're taking the sine graph, and for those of you that remember transformations, what are we doing with that sine graph? Left 30 degrees. That's it. That's the only difference. So you have your original sine function. And again, if you want to graph these, you could actually graph your original and then just take that entire graph and move it over 30 degrees. Now here, my scale, each of these, obviously, I think count 90 degrees. So the blue graph is sine x, and then you shifted it left 30 degrees. There's your new graph. Okay. Just take all your points, move them left 30 degrees, move it left 30 degrees, move it left 30 degrees, finished. What would this one, Mary, what was this minus pi over 6? How would that move it? The right, how many? Good. So it's your original cosine function. Simply move to the right 30 degrees. Got a couple of transformations here. Y equals cosine of x minus pi over 4 plus 2. Parker, what's the minus pi over 4 going to do? So right 45 degrees. And go ahead, Parker, what's the plus 2 going to do? So we have our cosine graph moved to the right 45 degrees, moved up 2. Now let's go through all of our different things. Let's talk about our domain range. Let's see, what was it? Domain range, period, and amplitude. First off, does our domain change? No. Our graph stretch from negative to positive infinity. If you move it over 45 degrees, guess what? It still stretches from negative to positive infinity. And if you picture that, you're thinking, but does it not move? No, it's forever. Okay. Range. Before, this one's a little bit tough. Before your range ran from -1 to +1, but you moved it up 2. You move that whole graph. Again, think about that box that ran from -1 to +1. And you take that box and you shift it up 2 units. Where does it run now? Say it again. Is it 0 if you move it up 2? 1, 2, 3. So -1 to +1 now runs from +1 to 3. Everything moved up 2 units. That makes sense. We're good? Let's see. So that was domain, range, amplitude. Did you change anywhere the height of your graph? No. No. The amplitude's still 1. And finally, the period. Did you? Let's see. I'll show you in a second what's going to change the period. But does it repeat the same over the same interval? You moved it up, down, left. It doesn't matter if you just move it. It still has the same interval of repeat there. So, same thing. You moved it left 45 degrees. You moved it up 1. That would change your range, and that would not change anything else. Okay, your amplitude's still 1. You can see that right here. There's the number 1 out front, so your amplitude is still 1. Domain still negative to positive infinity. The range is now 0 to 2, right? Because it was shifted up 1. Period still the same as well. Here we go. Graph 2 cycles of y equals sine of 2x and determine the period of the function. Amplitude is still 1. Okay, you're not going to change the amplitude at all, but this number 2 right here, what does that 2 do? Horizontal compression times what? Times 1/2. Let's look at your graph. The blue function is your original y equals sine x graph. Notice the sine of 0, 0, sine of 90 is 1, so on and so forth. What that 2 did, instead of repeating over that course of 2 pi units, it compressed it. It shoved it in some. You see that? So now your period is no longer 2 pi, but look what you got now. Yeah. It now repeats, if you look at the red one, it starts over here. Not here. Okay, it starts over in half the time. Because you compressed it by half. It's kind of like an accordion is what this reminds me of. So therefore, instead of 2 pi, and here's what you can do. Here's what you can do. Your original period, 2 pi. If you compress that by 1/2, your new period, pi. Okay. So what would change that period if you had a number in front of the x being multiplied or being divided? That's going to change the period of the graph. The amplitude does not change. The domain does not change. The range does not change. A number being multiplied by x would only change the period of the graph. Cosine 2x, what would be the period of that function? Same thing, right? Normally the period is 2 pi multiplied by 2. That's going to be a compression of 1/2. So that would be a period of pi. Might want to write this down. You know this, but honestly, sometimes I still use this formula. The period of a function, if it's in this form, y equals the sine of b times x, or y equals the cosine of b times x. Think about what that number b does. If a number is being multiplied by x, it's going to stretch or compress by a factor of 1 over b. You always have to flip when it's on that x, right? So instead of your period being that normal 2 pi, before when the number was 2, it compressed by 1/2. If the number was 3, it compressed by 1/3. So if the number is b, it's going to compress by 1 over b. So you're going to multiply that normal period of 2 pi times 1 over b, and you're going to get the new period of this function will be 2 pi over b. If there's a number in front of the x with both sine and cosine functions, the new period of that function will be 2 pi over b. And I know that you already know that, but again, here in a second, that formula is going to come in handy. I promise. Period is 2 pi over b. Determine the period of the following function. The cosine of pi over 2x. If a number is being multiplied by x, say it again. If a number is being multiplied by x, it doesn't stretch it by a factor of pi over 2. You always have to flip it, right? If it was 2/3, it'd be a factor of 3/2. If it was 1/2, it'd be a factor of 2. So therefore, this pi over 2 is going to stretch or compress by a factor of what? 2 over pi. So what you're going to do, you're going to take the period from before, which is 2 pi. The new period is going to be 2 times 2 pi over pi. The pi's cancel. What's the period? 4. So you now have here a function that's going to repeat not every pi, not every 2 pi, not every 4 pi or something like that, but every 4 units. I'll show you a picture. The blue, again, is your original cosine graph. And what you did, you took and compressed it like an accordion. And instead of repeating every, let's go crest to crest here. Instead of repeating every 2 pi units, which we keep saying 2 pi, y'all understand 2 pi is about 6.28. 2 times 3.14 is about 6.28 radians. It's now going to repeat hopefully every 4 units. Okay, this is 6.28. It looks like this thing repeats. Let's see, Chris. It looks like it repeats right here. Okay, which is, what did I say these were, 90 degrees. There's pi over 2. Pi, which is about 3.14. You see it's a little past 3.14. It's going to repeat every 4 units. Compresses it a little bit. Any questions? Sine of pi x. Your normal period is 2 pi, but that pi here is going to compress it by a factor of 1 over pi. Pi's cancel. What's the new period? 2. This function has a period of 2. Any questions on how I did that? So in review, now I do want to look at this. We won't go through all of it, but here's what I want to look at. That is the general form. We've not done all of them in the same problem, but that's the general form of an ugly-looking sine graph and an ugly-looking cosine graph. That's all the different transformations. For what we know, a number out front, what would that a do right there? Let's not read any of this. What would that a do? It stretches or compresses vertically. So it's going to change the amplitude. And it'll also change the range. Perfect. So therefore, these would have an amplitude of the absolute value of A. And they don't say much about the range, but you would pretty much just multiply your x and y values, or excuse me, multiply your beginning and end values of your range by that number. What would the B do? Stretch or compress horizontally, so it would change your period. Minus C would change, or what would it do? Good, or left. If it was a negative, if it was like negative, it would actually move it left. So if C is going to move it right or left, it won't change your domain because the domain's infinities. What would it change? X-intercepts. That'd be about it. It changed where your graph crosses the x-axis. And then plus D at the end is going to move it up and down. It's going to be a vertical translation. It would change your range, and that's it. Okay, so that's all the different things that we can do to it. We do know that A's and B's could be negative, and that would also flip it. Okay, we're going to know transformations for the years over, I promise. So let's put them all together, right? Determine the amplitude, period, and phase shift and sketch 2 cycles of this function. Y equals 2 times sine of 3x plus pi plus 1. I don't know, we told you about this before. I just want to remind you about it. We got a problem right here. Anytime a number's been multiplied by x, make sure that that number's factored out completely. So instead of writing it like this, we need to write this thing first as 2 times the sine of, and I'm going to put it in brackets here, 3 parentheses, x plus, I need to factor that number out. To get it in, I don't know if you noticed that, this form right here, it was b times parentheses stuff. So anytime a number is, in order to get the correct answers, in order to get the correct transformations in that HSRV order, make sure you factor that number out first. But 3 times what gives you pi? Pi over 3. Because if you multiply 3 times pi over 3, would the 3's not cancel and leave you with that pi? Think of it like this. If you, to undo a multiplication by 3, you would need to divide by 3. So kind of multiplying by 3 and dividing by 3, those two undo each other anyway and leave you with just that pi. So if you want to pull that 3 out, then you're going to have to divide by 3. And then you have the plus 1 on the end. Here's all of our transformations. Let's go through them. Autumn, what's the 2 do? Perfect. So the amplitude is now going to be 2. Everybody understand that? So first off, we stretch this thing vertically by a factor of 2. Raj, what's the 3 do? Horizontal stretch or compression. Is that going to be a stretch or compression? Compression. So it's going to change the period, right? The period is normally 2 pi, but you just compressed it by a factor of 1/3. So your new period is now 2 pi over 3. Makes sense. Didn't we say that the period of a sine or cosine function is always 2 pi over b? Right. The domain and range, hate to even put domain because it's always the same thing. Range. This is a nice one. You have two factors that's changing your range. That is, it's twice as tall and it's shifted up one. First, let's make it twice as tall. It used to be, the range used to be from -1 to +1. Somebody make it twice as tall for me, please. Good. -2 to +2. And then we shifted it up 1, so it's now at perfect. So the range is from -1 to +3. Can you use the range to actually find the amplitude? Yeah. Look at the difference in the range and split it in half. Okay. Any questions?
What does it mean by sketch 2 cycles?
Okay, good job. A cycle is a complete period. So if we look at the graph of this, make it repeat twice, which I sketched more than 2 cycles. I actually sketched, let's look and see, down, up, down, 1, 2, 3, 1, 2, 3, 4, 5. Yeah, I sketched 6 cycles of it. That's what a cycle is, a complete period. Now, the original I sketched 2 cycles of, but I'm an overdoer. I wanted to impress everybody about my ability to sketch things. So I sketched 6 cycles. And you see there everything that we just found. You see the amplitude, and again, the way I find amplitude is I find that point of equilibrium and I see how tall is it from there. In this case, my amplitude would be 2. You see the period, what was it, 2 pi over 3, which is, how many degrees is that? Pi over 3 is 60, so 120 degrees. This is 90. There's from 0 to 90, so it completes a full cycle over 120 degrees. The range, -1 up to 3. You see everything that we just covered. Okay. And it's another one. We're good with that. Just in case. First step, factor out the 2. 3 times the sine of 2 parentheses x minus pi over 2 minus 1. Stretch it 3 times taller. A half as wide. So the amplitude is going to be 3. The period is going to be half as wide, so the period's not 2 pi, but a single pi now. It's going to repeat every 180 degrees. We're going to shift it to the right 90 degrees. We're going to shift it down 1. Your domain is still the same. Your range, since we made it 3 times taller, would be from now, not -1 to +1, but -3 to +3. And then once you shift it down 1, it would actually be from -4 to 2. That's the new range. Any questions? Determine the amplitude, period, and phase shift, and sketch 1 cycle of that. Let's just look at the graph, because we know what's going on, right? The -3 out front, we know, is going to do 2 things. It's going to flip it and make it 3 times taller. The amplitude used to be 1. It's now 3. It's 3 times taller. Now it's shifted up and down. It's actually shifted down because that -1. So a combination of those 2 things is going to change your range. So you're going to make it from -3 to +3, and you're going to move down 1. So now you're from -4 to +2, right? -4 up to +2. The 2 out front that we're fixing to factor, x minus pi over 2. The 2 out front that you're going to factor is going to compress by half. So the period that used to be 2 pi is now a simple pi. So this thing should repeat every pi units. That's pi. That's 180 degrees. You're going to shift this thing to the right pi over 2. Well, that's weird. It doesn't look shifted. I wonder if I typed in the right graph. I don't think I did. Because that one's not shifted, is it? The red graph should be moved over to, let's see, pi over 2, which should be here. So take your red graph and now move it over, and that should be the appropriate graph. But it didn't change any of the other stuff, okay? Now what about this? What if this graph was moved over 2 pi? What if you tacked on like a plus 2 pi or minus 2 pi? Same graph. Because if you move it over to the right 2 pi or you move it over to the left 2 pi, does it not just kind of fall back into sync? So now I'm getting off on a tangent here, but we're doing sines and cosines. So if you took the graph of y equals sine x, and you took the graph of y equals the sine of x minus 2 pi. Same graph. That makes sense. Why? Because it would just line back up again. If you shifted it right 2 pi, since this thing repeats every 2 pi, it's going to line right back up. Okay? We've done enough of those. Let's talk about AM and FM. Talk about radio stations. Right? And this is neat because I wanted to throw this in. We're not real concerned with knowing this. Frequency, and you deal with frequency in science. Frequency is how frequently, well, it's really related to period because it's how frequently that sine or cosine curve repeats. So it's really got a lot to do with period, or how many times it repeats in a certain period. Sine waves are used to model physical phenomena such as radio, sound, and light waves. Before we start here, does anybody know what FM and AM stand for? FM, frequency modulation. AM, amplitude modulation. Here's how, which I don't think, yeah, that doesn't go into it. Let's talk about how radios work. You got your AM receiver here. And you tune your AM stations to a certain, you don't know that you're doing this, but when you're turning your AM station, you're tuning it to a certain amplitude. You know that? Now you know what amplitudes are. So what your radio station does, if you tune it to a certain amplitude, let's say that, you're not, but let's say you tune your AM station to 2, okay, just for simplicity reasons. What that means is your receiver is only going to receive sound waves of amplitude 2. Makes sense how it works? You're telling your radio only pick up all these frequencies that's in the air that's causing damage to our brain. You're only picking up the frequencies, not frequencies, don't say that. You're only picking up the amplitudes of 2. So certain radio stations broadcast at certain amplitudes. Well, what about FM? Okay, and first off, which is better? Amplitude modulation or frequency modulation? Hands down, frequency modulation. When you're dealing with FM stations, FM stations deal with, okay, only certain waves with a certain frequency. When you're tuning your FM station to 98.3, you're saying, I only want waves that have a frequency of 98.3 megahertz. Is that right? Okay. But anyway, only pick up those certain sound waves, and only those waves pick up on that station. So that's the difference between AM and FM, because we all know the sound travels in those waves, right? So sine waves are used to model these phenomena. A high-frequency radio wave is a wave that has a huge number of cycles per second. That's high frequency. So high frequency looks like that. Gets over and over and over. Lots of waves in a single second. A high-frequency radio wave is a wave that has a huge number of cycles per second. If we think of the x-axis as a time axis, then the period of a sine wave is the amount of time required for a wave to complete one cycle. We already know that. But if it was time, it would be the amount of time that it takes to complete a cycle. And the reciprocal of the period is the number of cycles per unit of time. So there's your actual frequency formula. Frequency is 1 divided by the period. For example, the sound wave for middle C on the piano is 262 cycles per second. That is the frequency, right? The sound wave, no, it completes 262 cycles per second. So therefore, the period of the wave is 260, because if it goes, yeah, the frequency is 262. If it completes over 1 second of time, there's 1 second. In that 1 second, it completes 262 cycles. That's middle C on the piano. So the actual period, how long does it take to complete 1 cycle? Would be 260 seconds of a second, right? And that's what it's going through there. So to make a long story short, frequency is 1 divided by 3. Problem. The normal period of a sine curve is 2 pi. This one has been compressed by a factor of 1 over 524 pi, right? Pi's canceled. Leaves you with 1 over 262 is the period. Everybody good with that? So the frequency is simply the reciprocal of that, 262. Frequency is 1 over period, period is 1 over frequency. What that means is, and if you're dealing with seconds, if your x-axis is in seconds, then this curve will complete 262 cycles in a single second. And what node is that? What frequency radio station is that? I don't know. What we're going to do now is, okay, we've studied all about, here's the curve, tell me everything about it. So now what are we going to do? We're going to make a curve. We're going to create a curve. We're going to be given the information, and okay, now what's the curve that fits this information? If you say 10 minutes after a furnace is turned on, the temperature of a room reaches 74 degrees. After 10 minutes, you're at 74 degrees. And then the furnace turns off. Sounds like at my house. And then it takes 2 minutes for the room to cool to 70 degrees. So after 12 minutes, you're at 70. And then the furnace kicks back on. And it takes 2 more minutes, for it to reach that 74 degrees. Do you see that periodic nature? Lots of things in our life, lots of things in the real world have this same periodic nature. That's a sine curve. Something heats up, cools down, heats up, cools down. Do you see the sine nature of that graph? So let's kind of sketch this thing out. I've actually got it already sketched to make it a little bit quicker. So here we've got at 10 minutes. I wonder where that's at on the graph. We can do it right here. At 10 minutes, you're at 74 degrees. At 11 minutes, you're at 72 degrees. At 12 minutes, you're at 70 degrees. And then it starts heating back up. At 13 minutes, you're back to 72 degrees. And at 14 minutes, you're back to 74 degrees. We want to try to fit a curve in this. Okay. And here's how you do it. First off, let's determine what is the period of this function and what is the amplitude of this function. Because that's 2 very important pieces. Okay? 2 very important pieces of your graph. What is the period? What is the amplitude? What do y'all think? Period. Is it 2 minutes? Let's see. It starts here. It goes down. Okay, it hasn't repeated yet, right? Comes back up. It's actually 4 minutes. Period equals 4 minutes. Everybody understand why? Because it was at 74. After 4 minutes later, it's back at 74. After 4 minutes later, it's back at 74. You see, how long does it take for it to repeat? So the period is 4 minutes. The amplitude, and again, the amplitude, think of it like this. You've got your highest temperature was 74. Your lowest temperature was 70. The distance between 74 and 70 is 4. So the amplitude is going to be half of that, or 2. Any questions on that? So you've got half your equation. Y equals, and you can actually model this with a sine curve or cosine curve, because we know sine curves, cosine curves are pretty much the same thing. Y equals the 2 times the sine x. And do you know why I put the 2 there, right? That's where the amplitude goes. If your amplitude is 2, stick it right there. Now let's think about our B number here. Because I told you this number right here is going to simply change the period. And if you remember a while ago, and I told you to write this formula down because I felt like it was going to make this a little bit easier. The period, nope, yeah, the period is equal to 2 pi over b. And in this problem, we're actually looking for b. We've got the period. The period is actually 4 minutes. So 4 minutes is equal to 2 pi over b. Right? Let's solve it like a proportion. Anytime that variable's on bottom, put a 1 on the other side. Solve it like a proportion. What does b equal to? Half pi. 1 times 2 pi is 2 pi. 2 pi divided by 4. Reduce 2 and 4, you get pi over 2. So the number that goes here is pi over 2. Now we need what we're going to add and subtract here. We need to know how far has our graph been shifted right, left, up, down. Has it been shifted over? Here's the easiest way to do it. But this is actually probably the hardest thing about this. Find you you remember what the sine curve looked like, right? Like that, right? And this point right here on a sine curve was 0, 0. You remember that? When x is 0, y is 0 on a sine curve. Find that point. Find a point to where, okay, my graph was coming down, and then it started going up. At this point of equilibrium, I've got a 0, 0. Well, find one of those points. Let's see, coming down, going back up, coming down, going back up. Is that not one of them? Y'all see that this point here corresponds with that point there? Come on. There we go. Graph's coming down, going back up, coming down, going back up. And my 0, 0 point corresponds with, in this graph, 1372. Now, is that the only one? Would it also correspond with, let's see, coming down, going back, this point? Yeah, there's infinite number of answers. You could shift this thing an infinite number of ways to get this answer. Now, up, no, you're shifting up 72. But you could shift left and right an infinite number of ways because we know this thing's periodic. So, originally, my sine curve crossed 0, 0. That was my equilibrium point. That was my middle point. But this one's been moved. From 0, 0 to 1372. And if I want to move that 0, 0 to 1372, what do I do to my x? Minus 13. And what do I do at the end? Moved it up 72. There's the graph. Now, let me show you this, and we're actually stopped with this. We won't have time for the second one. Here's how you check it. Clear? Let's type that in. Y equals 2 times sine x, and you probably need some double parentheses here. The sine of pi over 2, and then x minus 13. Plus 72. I think I got an extra set of parentheses in there. It'll tell me if I do. Maybe not. Of course, we can't see anything because our graph's been shifted up to 72. This is 10. So let's go from, let's see, our amplitude was what? What was the amplitude of this? 2. And my equilibrium point was 72. So let's go from 69 to 75 on my y. Window y's will be from 69 to 75. We should see some graph now. Might not be much graph. Yeah, that's not a very good graph. So let's change my window again. And think about, let's see, a complete cycle here. This was 1172. This was 13. Let's change that to where we get more stuff here. Let's go from 0 up to 40. Let's just see what that does. So 0 to 40 radians. Now I'm getting actually too many. Let's cut that down now. Let's go from 0. Well, we had from maybe 10 to 15. That probably look better. I changed my x. Yeah. So 10 to 15. There you go. Pretty good graph. And here's how I would check it if I were you. I'd go trace and type in something like 11. Look what I got. 1172. Type in 12. Go back to trace, type in 12. I got 70. Type in 13. I got 72. Do you see that fits perfectly? So now what can we use this for? Now that you've got your graph, well, what's the temperature going to be after 20 minutes? What's the temperature going to be after 30, 40, 50 minutes? You've got your curve fit. You know exactly what it's going to be.